For decades, researchers have believed that unencumbered, fully articulated 3D hand tracking will open the door to a new class of user interface. Such a technology will let users feel a visceral connection with their virtual hand, and a metaphor of direct physical interaction with the virtual world will free interaction designers to give us new user interfaces. We present a robust, efficient, long and short-range hand tracker which, while just another step towards this goal, has allowed us to prototype new experiences which help us to envision this radically new future. From direct analog input to physical interactions that come close to a haptic experience, our paper introduces the algorithmic tools required to deliver such state-of-the-art accuracy and efficiency. Our system takes 3D points directly from the depth sensor and fits a smooth surface model to the data using the Levenberg algorithm for energy minimization. We now slow the sequence down to see each Levenberg iteration. We see that, unlike ICP, our algorithm updates both correspondences in blue and pose in concert, meaning that 3 to 4 iterations are sufficient for accurate tracking. Reinitializer proposals in every frame mean that we can quickly recover from tracking failures. We compare quantitatively to other trackers on standard test sequences, and our accuracy exceeds or matches state-of-the-art like the H-Track system from Tagliasacchi et al. Comparing qualitatively to their work, we see that on high-end hardware, both systems cope well with low occlusion and struggle with fists. Our reinitializers allow for slightly quicker recovery from tracking failure. Our true advantage over H-Track is in greater efficiency, stemming in part from faster convergence joint optimization yields over ICP. This is despite the use of a more detailed, smooth surface model rather than just a collection of cylinders. Further efficiency comes from massively subsampling the data, which surprisingly yields very little impact on accuracy. This allows us to run the tracker on just a lightweight tablet. With its quest for efficiency, it may appear surprising to insist on a smooth surface model, but the smoothness of the model is necessary to allow the use of the Levenberg algorithm. Robust performance requires a strong reinitializer to complement the tracking component. Our work has reduced, but not eliminated, the limitations that hand trackers have been struggling with since 1993: occlusion, segmentation failure, and noisy data. Nonetheless, we believe the components we describe will form an important part of future real-time tracking systems. We conclude with a collection of experiences. Our primary user interaction paradigm is direct physical manipulation of virtual user interface elements, such as buttons, dials, sliders. Anything the designer feels might leverage the user's real-world experience. Even without haptic feedback, this is a compelling experience, and users report a real sense of ownership of their virtual hand. The use of paper-thin elements provide proxy haptics that further embed this illusion. This metaphor makes it simple to implement a computer keyboard or piano. Less physical concepts like laser fingers and pointing and clicking are also surprisingly easy to pick up. Direct analog input is also useful. Here the hand position and orientation control a spaceship, while other prototypes have mapped the user's thumbs to a game controller thumbstick. In this two-handed interaction, the subdominant hand holds a palette, while the dominant hand controls both position and brush size as analog inputs. The final sequence is of a video game created by a team of just 3 master students using a Unity plugin built on this technology. The user is huge, a giant character whose hands interact with the world to help the game characters achieve their goals. To conclude, we believe that our introduction of smooth surface modeling and joint optimization of both hand pose and correspondences will prove to be a key enabler to future hand tracking-based user interfaces.